Give me a second. Okay. Hi everyone. Thank you very much for introducing yourselves. I appreciate it. So, about this course. So this is statistical machine learning, and what do we do? So it focuses on statistical machine learning, which is almost most of the machine learning without a deep learning approach. Okay. And it has a theoretical approach, but we try to make it also practical, useful for practice as well. So I can say that by passing this course, you will understand how machine learning models are working. And so what do? We start with preliminaries, background, and then the mapping model. I will talk about it, and some tasks in machine learning, such as what is regression, classification, clustering, and these things. And then we will briefly cover overfitting and cross-validation. I might go a bit faster over these things, but I will cover it. And then regression models. We'll cover linear regression, including the regular linear regression, ridge regression, also lasso regression. Then classical classification methods. I'm sorry, by the way, I forgot to. There's. Yes, we'll cover classic classification methods, including LDA, QDA, SVM, kernel SVM, Bayes, KNN, trees, and random forest. We'll cover bagging and boosting, specifically AdaBoost. And then we'll cover mixture distributions, such as Gaussian mixture models. In the meantime, we'll cover point estimation, such as maximum likelihood estimation and expectation maximization algorithms. Don't worry, I will cover in a way that you understand. Then we'll go to feature extraction and dimensionality reduction. So we'll cover spectral and probabilistic feature extraction. We have at least 3 categories, 3 to 4 categories of feature extraction. One of them is spectral, one of them is probabilistic, the other one is neural network based, which is not covered in this course. It's not a deep learning course. No, there is a 4th one, which is Riemannian dimensionality reduction, also out of the scope of this course. But we'll cover spectral and probabilistic feature extraction, including PCA, FDA, MDS, multidimensional scaling, isomap, LLE, local linear embedding, variational invariance, factor analysis, probabilistic PCA, TSNE, UMAP, and metric learning. If time allows, we might cover other things such as random projection as well. And again, if time allows, some other topics we can cover, such as clustering algorithms, different clustering algorithms, such as k-means, DB-scan, probabilistic graphical models, including Markov models, spectrographs, hidden Markov model, Markov chain Monte Carlo, MCMC, causal invariance, if time allows, and outlier or anomaly detection, such as isolation forest or some other techniques, such as one class SVM and these things. This is a tentative schedule of weeks. You can see it in the outline, but again, I don't restrict myself to do the exact schedule. We'll see how it goes. Okay. About the course materials. So lecture notes will be provided to you. I will upload the lecture notes to a course link. I'll try to upload them before the classes. Also, after the classes, I will upload annotated slides. We have a YouTube channel of the course. I usually record my lectures and I put them there. So far, I have put three previous courses. One of them was optimization techniques, which covered classical optimization. Almost everything that I knew in optimization. So I think it's a good thing you can watch. I believe you will learn a lot from that course as well. Then I also have put the statistical machine learning and deep learning course in the previous semester, this YouTube channel. In this semester, I'm teaching three courses, two courses in University of Guelph, statistical machine learning and deep learning. I'm putting them in the YouTube channel. There is a third course in University of Waterloo, but that's the fourth year of undergrad. That's adaptive and cooperative algorithms. And in that course, which I also put in the YouTube channel, feel free to watch if you would like to learn about them. I will cover in that course, I'll cover meta-heuristic optimization, then the fundamentals of game theory, fundamentals of reinforcement learning, and fundamentals of fuzzy logic. So basically that course is kind of soft computing, that course. So I will put all of these under my YouTube channel. And I think it will be useful for you guys to watch later again, and also for the world to watch. And yeah, feel free to subscribe and recommend the channel to others also. Also have written some tutorial papers. Feel free to go and see them. Many of them are covered in this course. Yes. So I write tutorial papers sometimes with some co-authors and I put them on archive. Some of them have become the chapters of a published book. We have written a book named Elements of Dimensional Reduction and Manifold Learning, published by Springer. So feel free to take a look at the tutorial papers. Additional resource for interested students, Professor Ali Qudsi's lectures at the University of Waterloo. He has put them on YouTube. Check out his YouTube channel. I think his lectures are great in both statistical machine learning and deep learning. Also dimensional reduction. Additional books, again, these are not mandatory, optional if you would like, but you can take a look at them. They are available at the university's bookstore. I ordered them, so they are available there. So one of them is Elements of Dimensional Reduction and Manifold Learning, Springer. I'm one of the co-authors. And also Bishop's book, Pattern Recognition and Machine Learning by Springer. Also the Elements of Statistical Learning, Data Mining, Inference and Prediction by H.T. Tibshirani and Friedman. These are famous people in Stanford who are working on machine learning. The breed regression and these things, lateral regression, I think proposed by either Hasty or Tibshirani. I think Tibshirani, lateral regression. So these are, as you see, fundamentals of machine learning. They have worked on. And also there are a lot of research articles in the literature. So these are the course materials. But again, the lecture notes, I believe they are self-explanatory. The other things are for more information. Introducing myself, so I'm Benjamin Gojov. This is my email address at the University of Guelph. The course, this course and also the deep learning course does not have any TA in this semester. It had TA in the previous semester. This semester it doesn't have. The reason is that according to the rules of University of Guelph, classes which have less than 30 students don't have any TA. Okay. This course has, I think, currently 14 students, and deep learning course has 26. So, yeah, but that's fine. I'll try to handle it. But there is no TA in this course. In this semester, last semester it had. Last semester it was both courses were about 50 people. And both courses. Yes. So classes will be in person. And discussion chats and questions will be in Microsoft Teams group of the course. I will make a Microsoft Teams group and I will invite you there. So please join. Also, whenever you want to, I will make a question answering part in that Microsoft Teams group. Feel free to ask your questions there, but please tag me or mention me by at sign Benjamin. If you don't do that, unfortunately, my Teams has a problem. It doesn't notify well. So please tag me. Otherwise, I might not even find out that you have asked a question. Also, you can tag everyone by tag the name of the group, such as the tag question answering. Then it will notify everyone. The course's website, I haven't yet set it up, but I will do it soon. This is the course's website. I usually have for each of the courses that I have, I put a public course website. Why? Because it needs to be accessible by everyone in the world. However, I seldomly update it. So I frequently update the course link, but I do it here with lower pace. So, but yeah, I think for you guys who have access to course link, just check the course link. I will also upload the videos to YouTube channel, as I said, and I will eliminate personal information of the students. Okay. About course evaluation. So I have slightly changed the course evaluation in this semester simply because we don't have any TA. But first off, I think you might have heard. If you haven't heard, I'm a good grader. Yes, if you don't believe me, ask all of the students in the previous semesters in this university. I have given very good grades. If required, I will curve the grades at the end. And also, usually my midterm exams are straightforward. I try to make them not exactly, but similar to the pattern of the assignments. Also, I will be present in the exam. So if you have any question or clarification, you can ask me. So you don't need to worry about your grades. And there is a philosophy behind that. Several philosophies at least. One thing is that when I was a student, usually there are two kinds of instructors. Either they teach good and they grade very bad, or they teach very bad but they grade good. I try my best to have the best of the two worlds. I want to teach good and grade good. So this is my one of the philosophies that I have. At least I try. The other thing is that I want you to enjoy the course. You shouldn't go to the classes and pass the courses just for the grade. I think this is the wrong philosophy that has dominated the academia, unfortunately. It shouldn't be like that. You should only enjoy the course. I don't know if you have watched any YouTube courses. For example, have you watched, for example, physics of Stanford on YouTube or in MIT, right? If you watch them, how do you watch them? Do you care about your grade when you are learning? No, exactly here when you are participating in the class and you're learning, you shouldn't care about the grade. That's one thing. Again, the only philosophy of the course is enjoying and learning. Okay. Also, the exams will be open book. Why? There is another philosophy. I hate memorization. I don't want you to memorize anything. Just understand. Memorization as things meaningless. Okay, don't memorize anything. Just try on this. But it doesn't mean that you should study during the exam. You will face lack of time. You should understand well and then do the things in the exam. Okay. So as I said, I have slightly changed it. So I have removed the grade for assignments because there's no one to grade the assignments. I will not have enough time to do that. But I will post the assignments. So I will give you, I think, 2 assignments during the semester for you to solve it for yourself. And then I will give it due date. There's no Dropbox for uploading it. You solve it until the due date. I will publish the solution key to the course link after the due date, and you just check your answers. And I strongly recommend that you do the assignments, because in this way you will learn better. Also, the exam has the same approach. That's one thing. The midterm exam now has 50%, and it will be in the middle of the course, sometime in the middle of the course, in the middle of the semester, I mean. But the exact date, I will announce it. Apparently, I'm not sure. I was checking the calendar. I'm not sure. Do we have a fall break or reading week? Do we have? Is it a total week? Only 3 days or something like that.
No, it's a week.
It's a week. I need to double check the calendar again. Okay. So, but depending on when they put the reading week, if it is exactly in the middle of the semester, I will put the midterm exam after the reading week. But if it is too soon, maybe we don't put it after the reading week. When is that? Do you know? Okay, that's fine. But yeah, anyway, I will let you know about the midterm exam by also in the classes, also, and by making announcements in the course link. Please check your notifications in the course link. I will make announcements there. And we'll have course project. So the course project itself has 40%, and its presentation is 10%. Okay. So it's group projects. You will form groups. The number of people in the groups varies in different semesters. I will decide about it after the course has settled down. Unfortunately, there is some rule in University of Guelph that is weird, and is that students can drop any time until the end of the semester. You can't see this rule in other universities, but this means that we never can ensure that this is a final number of students in the course. But anyway, we'll assume that no one will drop afterwards. After that, we finalize the groups. That's one thing. And yeah, sometime in the middle of the semester, I will ask you guys to form teams of specific number of people in each team, and then you will have maybe 1 week to do the proposals and write the proposal. Proposals will not be graded. It's just for verification. Okay, so you don't need to put a lot of time on that. Write 1 or 2 paragraphs of proposal and what we are going to do. This is it, and you just upload it in the Dropbox of the course link that I will put, and then I will check it, and if it's good, I'll say okay, go ahead. And you will have time until the end of the semester to do the course project. In the last day of in the last class, actually, during the class time, you will present. And here, the group presentation. Everyone in the group is supposed to present, and then we will give feedback. And others will give you feedback. Then you have about 10 days after that to apply the feedback and modify your project, finalize it, and then submit the report and codes, everything to the Dropbox of the course link. So as I said, report, doing the project, report, code, everything. These are 40%, and the presentation is 10%. And by the way, the midterm exam will also be one of the classes. I mean, in the class time. Why? Because I respect your schedule. I don't want to change your schedules. But we know that in the class time, everybody is free at least, because they should come to the class. Also, bonus points for people who participate in the class, participate in the discussions. Please participate and ask questions, answer questions. You don't need to raise hand. Just interrupt me, and don't see me as a professor or something. See me as your friend. Okay, we are gathering to learn together. Don't see me as any professor. Call me Benjamin, Ben, whatever you want. And yeah, so as I said, feel free to participate in the discussions, interrupt me, and yeah, this is very important to me. Please participate. And also, by the way, why we don't have any final exam, as you see. There is a reason for that. Because I want the exam to be easier. And usually the course, when it goes further and further, it might become more and more difficult. So I want the easier parts to come to the exam. That's one thing. Also, I have seen that some in the previous semesters, usually people don't come after the midterm exam. Please come. Okay. If you don't come after a midterm exam, I suspect that, are you studying for grades? I said I already give you the grades, so why are you bothering? By the way, when I say I'm a good grader, it doesn't mean that you should become lazy and don't do your things. I mean, I'm a good grader if you do your best and do all of the tasks. Okay? Then I will give you good grade. Don't worry about that. I will, if required, I will curve the grades. Do your best and just enjoy the course. And please, I appreciate it if you come after the midterms. Last semester, there were 50 students. One time I came to the class, no one was in the class. I had to teach an empty class. But after a while, people came. Don't worry much about your marks, as I said. I give good grades. Focus on understanding the materials of the course. Our goal is to learn important practical and theoretical algorithms useful for both industry and academia. We'll learn some theory and also some in practice. And please ask questions and participate. I want it to be discussion based. I don't want to be the sole speaker. Okay. Any question? Any comment, question? No? Okay. Thank you. So,
Hi, Ben.
yeah.
Could you please put the date for the midterm earlier?
Earlier?
Yeah.
Sure, I will. But I can't right now, but I'll try my best. I'll try my best. But do you know, I need some time before I can decide about the midterm date, because I need to see how much I can cover until then. That's the reason I don't announce it at the start of the semester. Please give me some time so I see how fast we can go, and then I can decide about the time, because I want to cover some things before the midterm exam. Okay, thank you. But I will try my best to say it soon, as soon as I can. But it must be sometime in the middle of the semester. Okay. By the way, did I say that we have breaks in the middle of the courses? And usually we stay until the end, okay? Because we need to cover a lot of things. We usually stay until the end, but we'll have breaks. So I said this now preliminaries. Okay. Okay, data set, learning model, and learning tasks. By the way, wherever you don't understand anything, please feel free to ask and let me know. So, data set. Consider the measurement of a quantity. This quantity can be different things such as health data, like blood pressure, blood sugar, blood fat, images of a specific scene, what taken from a different perspectives. So for example, you have cameras taking pictures from something, from a sculpture, for example. Images from several categories of animals, such as cat, dog, frog, etc. You can have medical images. So, medical, right? Medical images such as digital pathology, also called histopathology images, including both healthy and tumorous tissues, right? Any other measured signal can be, right? And this quantity can be multidimensional. What do I mean? Can be when we say univariate or one-dimensional, it means that it's just a scalar. But multidimensional, it can be a vector, right? Multivariate or multidimensional. It has a set of values. Therefore, every quantity can be considered as a multidimensional data point in a Euclidean space, right? Euclidean space is the regular space that we usually learn in also high school, as a Euclidean space. Let the dimensionality of this space be D. So, for example, this is one-dimensional Euclidean space. Okay. Point, this is a scalar. This is 2D, dimensional. This is 3D. We can represent every point in this space here in a 3D, the 3D point, right? And then for the above, you need to imagine it. Okay. So we denote this D-dimensional Euclidean space by RD. R stands for real, because usually we work with real data. You might be working with complex data, but not at least in this course. There are some things that are, I think, advanced, much more advanced, such as quantum machine learning and these things. You might want to work with complex data. But here we are working with real data. So, and these values of the vectors, they are called features or dimensions of the quantity features. For example, you can have a vector of health data, such as a vector of blood pressure, blood sugar, blood fat, and each of these is a feature. You can have multiple measurements of the quantity. So, for example, you get my health data, your health data, the other person's health data. So each of us has some vector. Then you put all of these vectors next to each other, you will have a data set, a set of data points, a set of data vectors. By the way, when I say data vector or data point, they are the same, or data instance. Why? Because in the space, every point, every data point can be represented as a vector. Why? So consider this point. This is a 3D point, right? X, Y, Z, for example. But you can consider it as a vector connecting origin to that point. And this is exactly this vector. And as I said, when we have several data points or data vectors, then it's called data set. For example, the quantity can be an image whose features are pixels, right? Pixels. So D here is the dimensionality is the number of pixels. The number of pixels. The data set, and you might be wondering, how is it a vector? Because you can reshape it. An image to become a vector. The data set can be a set of images from a specific scene, but with different perspectives, for example. Then it becomes a data set. So we talked about data set. Now let's talk about the learning model. consider a data set of n data points. What do I mean by this? Xi is the ith data point, and I'm saying that I goes from 1 to n. So it means that I have x1, x2 until xn, and each of which is a d-dimensional vector. Right? So this is a data set, and each of which is a d-dimensional vector, as I said. In the d-dimensional Euclidean space, we can put them. Do you agree that we can put these vectors next to each other to become a matrix? I denote this by capital X. And it's d by n. Why? Because I'm putting them column-wise next to each other. Each of them is d-dimensional vector, and I have n of them. It will be like this. Right? By the way, in this course, I usually denote scalars by small case, vectors by bold small case, matrices by bold capital case, and sets by fancy capital case. For example, like this, something like this. Okay. And so yeah, this is my notation. So now consider a learning model F. I'm defining it now. What is it? It's a map. Map is something mathematical, some mathematical concept. It maps some, I think by its name it's obvious. It maps something to another thing. Okay. A map can be a function, but not all functions are mapped. Okay. It's a map from data space to some output space. So it takes some point in RD, d-dimensional Euclidean space, and it outputs a p-dimensional vector. RD to RP. It takes X and it maps it to f of X. Okay. Usually, but not always, usually P is less than or equal to D. It means that usually the output of this learning model is less than the dimensionality of the input, usually. So if you want, I want to illustrate it, it's like something like this. You have a box, a model F. You take X as input, and you output f of X. Here, I'm showing the dimensionality by the length of these lines, right? All of the machine learning models, you can see them as this learning model. Now, the whole thing in machine learning and deep learning is how to find or how to tune the parameters of this F to map X to what we want. X is the input. Let's tune this so it outputs what we want for every X. Okay. Now, according to learning tasks, we can have different learning models. So consider the learning model that we defined in the previous slide as a newborn baby. It's just born. It first knows nothing. And we should teach it. Okay. Now, forget this slide and listen to my story. So soon, I have a newborn baby. I want to teach it cucumber and tomato, or cucumber and apple. Doesn't matter. Cucumber and tomato, cucumber and tomato. Then what do? One way is that I bring several cucumbers and several tomatoes, and I say, take one of the cucumbers and tell the baby, hey baby, this is a cucumber. And take another cucumber, show it to the baby, that this is a cucumber, this is a cucumber, this is a cucumber, right? Then I move on to the tomatoes and I say, hey baby, this is a tomato, this is another tomato, this is a tomato, right? I show several samples of the cucumbers, several samples of tomato. Then I after this, let's call it training. I trained the baby. Then I come to the test phase. I say, now I get one of the cucumbers and I show it to the baby and I say, what is it? The baby will say, this is a cucumber. I take one tomato and show it to the baby. I ask, what is it? It will say, this is a tomato, right? This is called classification. Why? Because I'm showing the baby the classes of cucumber and tomato. Now, by the way, after this training, if I show the baby a carrot and I ask, what is it? What will the baby say?
Nothing. No.
What?
Nothing.
Oh, the world of baby currently is only the world of cucumbers and tomatoes. So it will answer it's a cucumber because it has only seen cucumbers and tomatoes. The carrot is very similar to cucumber. So it will answer it's a cucumber. And if I show the baby an apple and I say, what is it? It will say this is a tomato. Yes. Okay. If I want the baby to learn also cucumber, I need to add another class of cucumber. Carrot. I say, this is a carrot, but that was a cucumber. That was a cucumber. Then the world of baby will add the class of carrots to its knowledge. Okay. So that was called classification. Now, in another scenario, I have the same baby doing nothing. I want to teach the baby again cucumbers and tomatoes. Or I do another approach. I use another approach. I bring a lot of cucumbers and tomatoes. I shuffle them, put them in front of the baby. And I say this time to the baby, hey baby, I trust your understanding. I respect your understanding. I don't want to teach you. I respect your understanding. Based on your own understanding, try to separate these into two groups. Then the baby will take a look at them, thinks a bit, and say, okay, these are very similar to each other. These are green, they're lengthy, so let's put them next to each other. By the way, these are mostly red, they're round, so let's put them next to each other. And the baby say, okay, I could group them into two groups based on their patterns. This is called clustering because we are grouping them into several clusters. And now, if I ask the baby, hey baby, what is the name of this group? For example, I point to the group of cucumbers. And I say, what is the name of this group? What will the baby answer to me? What? They will not know. The baby will not know. Why? Because it doesn't. The baby doesn't care about the name at all. Only cares about the pattern. It might say the name of that thing, which is cucumber. Its name is Benjamin. Doesn't care, right? Also, it doesn't care that the name of that group is tomato. It can call it desk. Okay. The name here in machine learning is called label, right? So in the classification, I told the name or the label to the baby. And in that case, by discriminating, it could know the name of the group also. However, in clustering, we don't have any label. We don't have any name. We only group them by their patterns. That was clustering, the difference of classification and clustering. Now, let's move on to another example. So, I want to train some artificial leg. Yes. Okay. For people who don't have any joint or leg, then what do? I can say, okay, let me go to a healthy leg, and I get I think ECG. Am I right? ECG. the muscle signals from the brain, or EMG, sorry, EMG is muscle. EMG signals for at the joint. Okay, then I say, okay, I will ask the person with the healthy leg, move your leg to different degrees that I tell you, different angles, and then I will measure the EMG signal. Then I will have a lookup table, right? Lookup table. Okay, this EMG signal is corresponding to this angle. This. Then I train a model to get this table and interpolate between them, and also extrapolate. Because for me, even if I go with fine steps of the different angles, I can't cover the whole angles, right? The angle is a continuous range. I have to quantize it. It's infeasible for me to cover the whole range. However, I can sample it with fine steps. And then let the regression model, it's called regression or prediction model, interpolate the table and extrapolate. The whole art of regression is interpolation and extrapolation. Otherwise, the dumbest model can memorize a lookup table. We need to interpolate and extrapolate correctly. So then, when I can interpolate, for example, in the training, I trained in the lookup table. I had 40 degrees and 45 degrees for assume, and there was no angle between them in the lookup table. Now I put the artificial leg on the person without any leg, and I will get some signal which is corresponding to 43 degrees. Then the model will understand that this is corresponding to 43. Why? Because this is kind of between 40 and 45. That's called regression, also called prediction. So regression is another name for prediction. You're predicting, right? Another example is weather prediction. Based on different features of the city, pollution and different things. What will be the weather of tomorrow? Another example is stock prediction. So usually time series predictions are regression also. But for regression, you don't have to be time series, by the way. So we covered regression classification. Oh, another example. Now consider another scenario. I want to teach a dog. How do people teach animals? Do you know that? Assume I have a dog. I want it to learn that whenever I come to the house, it needs to come and hug me, or it needs to come to me. Once I come to the house, it doesn't come to me. And I don't give the dog any sweets. So I kind of punish it, right? Then the next time I'll come, the dog randomly comes to me. Random. I give the sweet to it. And the dog, after some trials and errors, the dog will find out that apparently there is some correspondence between coming to me and eating sweets, right? Therefore, the dog will try, for having the sweets, it will try to do what it has interpreted, coming to me. Okay, this is exactly what we do in reinforcement learning. In reinforcement learning, we assume that the machine learning model is a dog. Okay. And then by giving positive rewards or sweets and punishments or negative rewards, we'll teach the dog or the machine learning model to do what we want. Initially, it will try and do some things randomly, right? But by these random trials and errors, it will find out that, okay, some things are corresponding to the positive reward. So let me do them in those situations, right? So in this case, it will try to do the correct things in those situations. And in this way, it will learn perfectly, almost gradually. Initially, it's very random, but gradually it will be very well that it can even play Atari games very well. This is reinforcement learning. There are some other concepts too, but let me, before going to the next slide, let me go into the math a bit. So regression, in regression, f of x, the output is continuous. In regression, as we talked about, it's continuous, right? So for example, some examples can be some continuous range between 0 and 1, p-dimensional vector whose values are between 0 and 1, or it can be real value, right? In classification, however, the output is usually finite and discrete. Here, for example, we have M classes. So kind of, you can see classification as a special case of regression. In clustering, we have, again, M groups, but you don't care about the labels. You care about separating them. In reinforcement learning, your machine learning model should give you some action based on some policy. Let's say, in this situation, X, assume your input is the environment. This situation or environment, what should I do? What action should I do? And this A, capital A, is the action set, possible actions that it can do. Okay. So give me some action. Now let's go to other learning tasks. Then dimensionality reduction and manifold learning. They're used interchangeably. Manifold learning is usually used for nonlinear dimensionality reduction. What is that? It takes a d-dimensional vector and it outputs a p-dimensional vector where p must be less than or equal d, and usually p is much less than d. Much less than d. Hence the name dimensionality reduction, because we are reducing the dimensionality of data. Right? Why do we do that? In unsupervised cases, by the way, when we have labels, forgot to say, when we have labels, it's called supervised. When we don't have labels, it's called unsupervised. So, for example, regression and classification are supervised because we have labels for it. We have continuous and discrete labels for regression and classification, respectively. But for unsupervised, we don't have any label. So for unsupervised dimensionality reduction, the goal is usually this. We want to we want to map the data points from high dimensional space to low dimensional space. Usually this low dimensional space is called embedding space. In this embedding space, my goal is that the similar points fall close to each other and dissimilar points fall away from each other. I think it makes sense, right? I want the similar points to be close to each other in the end. Let me learn some map. It does exactly what I want. Put the similar points next to each other and dissimilar points away from each other. This is the goal of unsupervised dimensional reduction. This goal, you can summarize it in this sentence. Fit locally, think globally. Okay? Fit, then locally, what do I mean? Locally, the points should be similar to each other. Right? Then, hopefully, the global structure will be preserved. In supervised dimensionality reduction, the idea is this. In supervised, now we have labels. We have some class labels assumed. Then what do? I want the points in the same class fall close to each other in the embedding space. And points from different classes fall away from each other in the low dimensional embedded space, right? The idea of, so in other words, I want the intra-class variances, I mean the variance of the points within the classes, to be decreased. And the inter-class variances, the variance between the classes, to be increased. So the confusion of classes gets less, right? The idea of unsupervised dimensionality reduction was mostly dominated and proposed by locally linear embedding, by proposed by Sam Royce et al. And the idea of supervised dimensionality reduction is mostly dominated and proposed by Fisher, Ronald A. Fisher. If you don't know him, just Google him and you'll see. You can see him as the father of modern statistics. He has proposed variance. Variance is proposed by Fisher. As many of his works were concentrated on variance. He has proposed variance, ANOVA, and different things, and Fisher discriminant analysis. These are related to variance. He was a scientist in genetics. Okay, for more information on dimensionality reduction, you can see our textbook. I think if you go by the university IP or VPN, you can access it. You can access the PDF. Numerosity reduction or numerosity processing, sorry. So these are less well known in machine learning, but you can see them as learning tasks, kind of. So outlier or anomaly detection, we detect outliers in the data. Why? Why do we want to detect outliers in data?
They can change our outcome if we enter them in our processing or learning model. Okay, so you're saying that, I'm repeating this to be recorded. So you're saying that because if we incorporate them in the training, so it will ruin your model, right? It will ruin it. Yes, that's correct. This is one of the reasons that we might need outlier detection for removing outliers from data. There's another reason that we might need outlier detection too. What if actually outliers are important for us? So in the previous reason, outliers are ruining, are not good. We hate them. The second reason, we love them. Want to find the outliers, such as credit fraud detection. Frauds, they are outliers, but we want to find them. Sometimes, actually, the outlier is the goal. For these two reasons, we need outlier or anomaly detection. Also, we have these prototype selection and prototype generation, usually less well known. By the way, when I say numerosity, I mean, so the number of points is numerosity, the number of features is dimensionality. Right? So these algorithms are working with a numerosity. So prototype selection is selecting important instances, important data points, kind of opposite of outlier detection, right? So let me find some representatives of data. This is called prototype selection. You can use it for numerosity reduction, reducing the number of data points. I think it's actually important. Why? Because in this time of big data, what if your model can't have all of the data? You need to throw away some data points. Which ones are less important? Prototype generation is prototype selection plus something else, plus generating some important points too. So selecting important points, also generating some more. So for more information on these, you can also see, for more information on both dimensionality reduction and numerosity processing, you can see my PhD thesis. We have some other fields of AI. We have soft computing, mostly covering these two broad things, fuzzy logic and fuzzy control, also meta-heuristic optimization or an intelligent search. So what are these? Fuzzy logic kind of stands or is a protest against binary logic. So binary logic is that are you feeling well? Well, I ask you, are you feeling well? You might say yes or no. I'm feeling well, I'm not feeling well. This is binary logic. But what if you say, I'm 70% well? I'm neither well nor bad. Okay? I'm 70% well. So you want to give me a range, a percentage or something. And that's called fuzzy logic. So it becomes fuzzy, right? It's not 0 and 1.
And it has been used a lot in control theory. Fuzzy control, especially in Japan, is used a lot. Was used at least. I think their subways were using fuzzy logic. At some point, I'm not sure about now, but at some points, or the reverse pendulum is used for NASA rockets. When the rocket wants to start going up, it shouldn't fall. Okay, so that at some point, I know NASA used fuzzy logic for that. Why? Because the University of Berkeley was funded for that to work on this project, and Lotfi Alizadeh, who was one of the founder of fuzzy logic, was on this project. And what is meta-heuristic optimization and intelligent search? So briefly, let me tell you. So when you have some optimization problem, what happens? So if it is easy or simple, you might have some constraints. Yeah, for more information, by the way, you can take a look at my YouTube channel for optimization course. But in simple words, in fast words, so when you have some cost function, you want to minimize it, you might have constraints or you might not have constraints. If you don't have any constraints, just you want to minimize some function, what do? You give me a suggestion. I want to minimize some f of x. Tell me.
Derivative.
Derivative, okay. So you take derivative and you set it to 0, right? You take derivative, you set. We learned this in high school or college, right? Take derivative, so it gives you the extremums of the function, right? So when you take derivative, you set it to 0, it gives you at least 3 points called the stationary points, either minimum or maximum or saddle points. They're all called the stationary points, right? And for finding out whether it's minimum or maximum, we can use the second derivative. Here, the second derivative is positive because it's facing up. Here, the second derivative is negative because it's facing down. Okay. But what if you take derivative, you set it to 0, minimize f of x with respect to x, you take derivative, set it to 0, you need to find some x, right? Equals something. If you can find it, it's a closed form solution, right? But what if this equation is too complicated that you can't find x in one of the sides of the equation? In other words, you can't find x as a closed form solution. What should you do? What?
Find some constraints.
Find some constraints? No, here we don't have any constraints. We don't need to add constraints. It's an unconstrained optimization problem.
We'll check after some point it will start increasing, like double derivative.
No, I'm saying that assume I do that. How can I find the solution when I can't find any closed form solution? That's fine. Tell me answers, and if it's not correct, that's fine.
We hit and try, we'll put in some values.
Yes, that's one way. That's one way that we put random values and see which one is the closest to 0, right? Something like that. But that's related to meta-heuristic optimization or some other things. We'll get to that. But now we are in the world of classical optimization. What should we do?
I was gonna suggest Newton's method.
What? Newton's method? Yeah, exactly. So in simple words, for solving this, when you can't find any closed form solution, you need to solve it numerically. Have you passed any numerical analysis course? Numerical analysis, the whole thing is this. You have some equation, you can't find its closed form solution or roots. Let's find it iteratively, numerically. Okay. So there are some techniques for solving this. If you use only first order derivative, it's called gradient descent. If you use both first order and second order derivative, it's called Newton's method, that he said. Right. Newton's method. Okay. Now, what if you have constraint? Now back to what you said. What if we have constraint. Minimize f of x with respect to x subject to some constraints. Right? How can we solve it? What? Draw a graph. Yeah, if it is 2D or 3D, I agree. We visualize it in the graph and we can find out the solution. Visualization for 2-dimensional or 3 dimensions is a good technique for finding solutions of optimization problems. But what if it's too high dimensional? If 100 dimensional? So there are several techniques. One technique is that we kind of bring this as a regularization term to the cost. Then it becomes an unconstrained problem. Okay, I'm saying this briefly. It's not related completely to the course, but we'll see a lot of examples like this in the course. Anyway, so one technique is this: we add the constraint, we incorporate it in the cost, right? And this is called regularized cost. Regularized cost. This term is called regularization term. Okay. And then it becomes an unconstrained optimization problem. Then back to what we had. Right? There are some other techniques which actually use the constraints. They don't do this. Such as interior point method. Interior point method is simply nothing scary. Very simple. It's Newton's method generalized for constraint optimization. Newton's method generalized for constraint optimization is called interior point method, also called barrier methods or log barrier methods. For more information on that, not required for this course. For more information on that, feel free to watch my videos on optimization techniques. Okay. Anyway, I said all of these to come to materialistic optimization. What if your optimization cost is too complicated? Or you have too many constraints? For example, you want to optimize the aerodynamics of an airplane or something like that.
Use random search method.
Exactly. Now you can do search. Let's not use the mathematics of optimization. Let's just search some solutions. Now for search, it has several subcategories. There are several methods. One of them is random search. Randomly you search, right? However, it's not accurate. What if you don't find the actual solution at all during your search? Another thing is brute force search or grid search. Now let's make this whole space into grids and go with fine steps and search all of the points. However, its time complexity is awful. It takes a lot of time. So we need a kind of a middle way case scenario. So what should we do? Let's search wisely. Or intelligent search. And that's called meta-heuristic optimization. An example is this. So we are in this room. And and there is some treasure in the ground of this room. But we don't know where it is. There are some people here. We want to collaboratively find the treasure. What should we do? Again, one way is randomly search, but it's not accurate. We might never find it. One way is grid search. It takes a long time. One way is wide search. So in the wide search, initially randomly we dig. I dig here, you dig here, you dig here, there. Then I find, for example, some plastic. You find some copper. You find some gold. Then we will announce our findings, and then I say, okay, I find this, you found this, and then we say, okay, apparently gold is more important than copper. Copper is more important than plastic. Therefore, the global best is gold. So we too, let's move toward that person, which is the global best, but we don't completely go there. Why? Because in the middle way, maybe we find something more important. Okay. So we a little bit move toward that person, and that person also searches locally in that area because that area is important. And then in the second iteration, we dig again. Then that person finds still some gold. You find something, maybe a plastic. Then I find some diamond in the middle. Then I said, I found diamond. Now we forget about the globe. We said now the global base has changed and this is diamond. So you two move toward me and I'll look around you. We do this until we finally collaboratively find the treasure, right? This is what the algorithm that I explained is called particle swarm optimization, one of the materialistic optimization methods, okay? So there are a lot of different algorithms for materialistic optimization. So these two, you can kind of see them as soft computing. For more information, you can see my course in Waterloo on soft computing. I'm putting them on my YouTube channel. So we have biological inspired neural networks also. It's related to neuroscience and cognitive science. Example is spiking neural networks. That's another category of the AI. We have feature engineering. You can see that's feature selection and feature extraction. So feature extraction, I already explained, is dimensional reduction, and feature selection. Let's select the most important features from the data. We also have application of AI in various fields of science and technology. Okay. So let's have a break and come back at 8:35. Yeah, and we'll continue. Okay, so let's continue. Let's continue. So let's go over these very fast. Okay, I think you know a lot of these things. I don't need to go over these very detailed, but I'll try my best to cover things. So expectation, variance, covariance, bias, and mean squared error. So consider what is a random variable X. It's a mathematical form for realization of a quantity which depends on random events. Okay. So we have discrete random variable and continuous random variable. So the discrete countable set of possible values. So it can take x1 to xm. Right? But continuous random variables is an uncountable set of possible values. For example, a range between 0 and 1. What is probability mass function? When your random variable is discrete, and its distribution is PMF, or probability mass function. For each of the values, it has some probability, right? And the summation should become 1. When it is continuous, then it's probability density function, EDF, and it's defined as this limit of probability x sandwiched between x and x plus delta x over delta x, where delta x goes to 0. So we have cumulative distribution function which sums the probabilities up to some point, and that's exactly it means this for all of the x's less than or equal to some x, right? So it's always either increasing or it doesn't change, right? So it can be like this, but it's always increasing. And expectation now. Let x be a random variable with probability mass or density function f of x, right? Then expectation, also called expected value, is the mean of distribution. So expectation consider the discrete data. Expectation for discrete data is defined as this. Denoted by E of x is summation of xi f of xi. So each xi that it can get times its probability. You sum them up, right? For continuous data, the summation becomes integral. When the summation becomes integral, they also call it Riemann's sum. And as you see, it's integral of x f of x dx. Okay, now consider h of x is a function on the random variable, right? So you get x as input, you put it as the input to the function h, and it gives you h of x. Then expectation of h of x, so as x is random, h of x is also random, right? So expectation of h of x, simply you put rather than x, you put h of x here. Right? Also, expectation is a linear operator. So expectation of summation becomes summation of expectations. Right? It's a linear operator. Expectation of summation of AI xi becomes summation of AI expectation of xi. I'm going over this fast because we need to cover a lot of things. Okay, so assume now variance. Variance is defined as this. Variance of an estimation x hat. If it's x hat, you can see it as a estimation of x. Okay, is the expectation of x hat minus so x hat minus expectation of x hat. What does it mean? So expectation of x hat is the mean of variance, mean of estimation. Okay, expectation is mean of estimate. By the way, there is a difference between mean and average. Average is a special case of mean, right? For example, if it is Gaussian distribution, then average becomes mean. So x minus expectation of x means that how much am I deviating from the mean? Okay. However, as I don't care about the sign, whether I'm greater than the mean or less than the mean, let's square it. And then the whole thing, this difference, which is the error, let's have the mean of that. The mean of a squared error. That's called variance. Okay. It's equivalent to this. So you can see it as a second the definition of variance. Expectation of x squared minus expectation of x squared. Okay. So proof, this is variance, right? So I'm using equation 9. I'm using the formula of binomial thing. A plus b squared is a squared plus b squared plus 2ab, right? So if you do that, you will have this term. As you have minus here, you will have minus here. Then expectation is a linear operator. So I can have it here separately. And these two, one of them with one of these terms cancel. So we have this. Right? Because what is this? This is minus 2 expectation of x squared. Right? Right? Okay. So we proved that that was variance. Now we have bias. By the way, usually in many interviews, they might ask you this in industrial interviews. Also in academia, if you have any background exam, they might ask you this. Okay. So these are important. Bias of x is expectation of x minus x. So how much am I deviating from the mean? However, here sign is important. Whether I have positive bias or negative bias. Okay. And I think using the dart example, you can understand it very well. So here in shape A, figure A, we have a lot of bias because we are very far away from the mean, actual mean. By the way, this is the mean of estimation, but this is the actual thing, x, right? It's not x hat. So the actual thing is here, and the mean is here. As our estimations, our darts, right? So there is a huge difference. So bias is high, however, variance is low. Because they are all close to each other. Okay. Here in figure B, variance is high. They're very far away from each other. These are, right? Variance is high. Bias is low, right? Because the mean of these is here. The actual thing is here. Difference between the mean of estimation and the actual thing is very small. Here in figure C, the variance is high, the bias is also high. Right? In figure D, both variance and bias are low. Right? Now, can you tell me which one is the best case? D is the best case because we want the variance and bias to be low. What is the worst case? D. Both variance and bias are high. If I'm a dart player and I do C, I'm awful player, right? Okay. Mean squared error, or MSE, is defined as this. So you have the difference between x hat and x. So how much am I deviating from the actual thing. Here I'm not using mean. For variance, we had the mean, right? X hat minus x. Now the sign is not important, so let's square it and then take the mean. Why? Because we might have several of them. We might have several data points, right? So this is mean squared error. And there is a relation between mean squared error, variance, and bias. Mean squared error is variance plus bias squared. Proof is here. So according to the definition of mean squared error, I have this. I use the binomial equation. So I will have this. Sorry, I'm not using binomial. So I'm subtracting expectation and adding it back. Okay. So then I use the binomial thing. So the first term squared plus the second term squared plus 2 times the first one, the second one. At the same time, I'm using the fact that expectation is linear. Okay. And here, give me a second. Okay, now I'm using the expectation is linear here. So I have the expectation of the first term. Now the expectation of the second term is itself. Why? X hat is random, right? X hat is random. Is expectation of X hat random? No. It's the mean of estimation. It's deterministic. It's not random. Therefore, expectation of X minus X is itself. And here, again, I'm applying. This one is not random, so it can come out of the expectation. So I will have expectation of only this term, third term, this middle term. Then again, I know that expectation is linear. So I will have expectation of X hat minus expectation of X hat, which is itself expectation of X hat. I'm saying this very fast. If you didn't understand, just go back in the video later, and I think you will understand what I'm saying. Simply, I'm using the fact that expectation of X hat is deterministic, expectation is linear, and I'm using the binomial equation. Okay, and then this becomes 0. So this goes away. Therefore, and interestingly, this is variance and this is bias squared. Okay, so we just proved that. So we can show this using Pythagorean theorem in a triangle, right? Covariance. Covariance is now between 2 random variables. Okay. Covariance between X hat and Y hat is defined as this. So we have X hat minus expectation of X hat times Y hat minus expectation of Y hat, and then use the mean, the whole mean. We can restate it as this. So covariance, you can see it as expectation of X hat, Y hat minus expectation of, sorry, this must be X hat times expectation of Y hat. Okay, proof. So I'm using equation 14. Now I'm multiplying the terms to each other. If you do that, you will have these 4 terms. Then expectation is linear. So I will have these terms. Then what happens now? This expectation of Y hat is deterministic, can come out of expectation. So we'll have expectation of X hat and expectation of Y hat here. Same thing here. Expectation of X hat is deterministic. Again, the whole thing here is deterministic. So now these two cancel each other, you'll end up with this, right? Right? Okay. Variance, if we have 2 random variables, so X and Y hat, variance of X hat plus B, Y hat is variance a linear operator? I think it's obvious because of the squared in the variance. Right? Therefore, you can't say variance of Ax plus By is A variance of X plus B variance of Y. If you solve it, I don't go through the whole details, but you can take a look at that. I think it's very straightforward. You will end up with this A squared variance of X plus B squared variance of, must be Y plus 2AB covariance of X and Y. So you will have a covariance term. Also, you will have a squared, b squared. Why do we have a squared, b squared? Because variance is quadratic. It has a square in it. If two random variables are independent, denoting by this, x and y are independent, then their covariance becomes 0. Here is the proof. Expectation of x, y, according to the definition of expectation, which we reviewed, you will have this. Now I have double integral. Why? Because I have two random variables. Then I know that this is a joint distribution between x and y. When two random variables are independent, I can write it as a multiplication of the probabilities. F of x times f of y. Okay. Then I can restate it, so I can bring one of the integrals here. This is integral over x. This is integral over y. Okay. Interestingly, this is expectation of x hat, and this doesn't depend on y hat, so we can bring it out. So it becomes here. Interestingly, this is expectation of y hat. So this is this. This equals this. Expectation of xy equals expectation of x times expectation of y. What was the definition of covariance in equation 15? According to this, covariance becomes 0. Covariance becomes 0. So when two random variables are independent, their covariance becomes 0. The other way around is not necessarily true. Okay. You might have covariance 0, but they might not necessarily be independent. We can prove it by a counterexample. So when you have, in general, when you have variance of summation of ai xi, is that you will have summation of ai squared variance of each of them, and ai aj covariance xi xj will have covariance terms too between each pair. Right? When you have covariance of summation of ai xi and summation of bj yj, you can see it is summation of ai bj covariance of xi xj. We are just simply extending equations 15 and 16 that we had in previous slides. And if xi's are independent in equation 19, then these covariance term, all of them become 0. So you will end up with equation 21. Right? Now, dependence and correlation. This is important. Consider two of us, me and you, for example. Assume I come toward you, you go away. I come back, you come toward me. In this case, we two have linear dependence, right? And this dependence is positive. But when I go this way, you also come this way. When I go that way, you also go that way. Your direction is the same as me. But this is linear. But this exactly is imitating what I'm doing. Now, so I come toward you, you come toward me in the other direction. I go back, you go back. So we still have linear dependence, but this is negative dependence. Negative linear dependence. In statistics, linear dependence is called correlation. So we have correlation. Now consider another example. I come here, you go somewhere. Come here, I come towards, you do something. Can we say we are dependent? How do you know that? How are we so sure about it? You're saying no, but how are we so sure? Maybe we are dependent, but it's so complicated for you to understand. Maybe we are not dependent and it's completely random. So finding out whether we are dependent or not is very hard. Therefore, dependence is much harder to find out than correlation. Therefore, you see a lot of correlation papers, science, you see much less dependence. Dependence is a general case. It can be non-linear dependence, right? We will see in this course, in supervised PCA, there is a major named Hilbert-Schmidt independence criterion that the technique is interesting. It says here in the input space, in the Euclidean space, calculating dependence is very hard. But we know calculating correlation is easy. Let's map or transform our data, in this case V2, to another world, another space called Hilbert space. We will talk about it, Hilbert space. In the Hilbert space, after this transformation, we calculate correlation, linear dependence, which is easy to calculate. That's a good estimate or approximation for nonlinear dependence in the input space, in the Euclidean. That's called Hilbert-Schmidt independence criterion, or HSIC. We'll see that. That's very interesting. See. Okay, so correlation, we have a famous correlation coefficient named Pearson correlation coefficient, and that's defined as this is covariance of x and y over square root of variance of x, variance of y. And this correlation is always between -1 and 1. Conditional probability. So the joint probability of x and y, it is probability of x given y times p of y, or p of y given x times p of x. I think it's obvious, its intuition is obvious. It means that what is the probability that y happens, and then given y, what is the probability that x happens? It's kind of sequential. Or here, what is the probability that x happens, and then given x, what is the probability that y happens? We have something named Bayes rule. According to just what I said, these two are equal to each other. Now let's restate this. Rearrange it. We'll have this. This is Bayes rule. Okay. Probability of x given y equals probability of y given x times p of x over p of y. And p of you there, and also according to what we just said in equation 22, if you put it in equation 23, you will get this. You can write probability of x given y as joint probability of y and x over p of y. P of y and x is equal to p of x and y, right? Doesn't matter. There are several, at least 3 laws which are important in probability. One of them is law of total probability, also called marginalization. What is that? Probability of y, you can see that as a summation of probability of y given x times probability of x over all of the x, all of the possible x. This is discrete, and this is the continuous case where we use integral. So here we are marginalizing over x, over possible values of x. You can do the other way around for y. You can marginalize over y. We have conditional expectation. Do you remember? We talked about expectation. Now this is conditional expectation. Expectation of y given x. It's just simple, very similar, but here rather than the probability of y, we'll have probability of y given x. Okay. Now the second important law in probability, law of total expectation, also called Adam's law. I will tell you why it's called Adam's law. You'll see that. This is the formula. Expectation of y equals expectation of y given x. Let's see the proof. Expectation of y, according to the definition, is summation of y fy. Fy is probability of y. Then fy, I can write it as a marginalization over x. Then what happens? I can bring this y inside the summations. Remove it. Right? What is this? Interestingly, this is expectation of y given x, according to equation 27. Right? Then, interestingly, this is the definition of expectation again. Expectation of y over x, but where this expectation is over x. Right? Do you remember? We had expectation of h of x. We can see this as h of x. Function. The third law of total variance, also called Eve's law. By the way, you don't need to memorize anything, right? Just try to understand and law of total variance, or Eve's law. What is that? Variance of y equals expectation of variance of y given x plus variance of expectation of y given x. So expectation variance, variance expectation. And now, why do we call it Eve? For you to remember. EVVE. Now that we call it Eve, let's call this the other law Adam and Eve. Hence the name Adam's law here. Okay. Here, Eve's law or law of total variance is this. Let's prove it. What was the variance? Variance of y is expectation of y squared minus expectation of y squared. I can rearrange it to be this. Now what? By law of total expectation, what was law of total expectation? I can write expectation of y as expectation of y given x. Here, I have expectation of y squared. I can write it as expectation of y squared given x, right? However, I know expectation of y squared equals variance of y plus expectation of y squared. Therefore, I can write it in this case. Variance of y given x plus expectation of y given. So I'm just adding x given x to the here. Okay. Hopefully there is no problem in the recording. Internet went off for a second. Just give me a second to figure it out. The worst case, I will present it rather than writing down. We had some fluctuation in internet. Fine. Did this stop showing?
Right.
Right. Okay. Hope that. Give me one second, no problem with recording. Okay, so my device had some problem now. When this happens, device stops working, but I can continue on the PDF. Nothing can stop us. I think it's a bit hot here. Let me open the door. Okay, so what were we saying? We were saying, sorry that I can't write down currently because of technical issue. So we were here, right? We were saying that, so we had expectation of y squared equals this according, so we were by law of total expectation, we had this. Now from the sides, I subtract expectation of y squared. Okay, then what do I have? So I'm repeating this term here. I'm repeating it here. And again, I'm using law, Adam's law or law of total expectation here on this, right? Then what happens? Then I know that expectation is a linear operator. So I can apply it on this and this, also have this term. These two, interestingly, is the definition of variance. Variance of this and this, right? So expectation of Benjamin squared minus expectation of Benjamin squared becomes variance of Benjamin, right? So we just proved Eve's law. Okay. Monte Carlo approximation. So suppose we're considering some d-dimensional data. X is d-dimensional. And let f of x be the probability density function of data. Consider h of x is a function, right, over x. Now, according to the definition, we saw that expectation of h of x, we saw that in previous slides, is summation or integral of h of x, f of x, right? Also, we have probability of h of z belonging to some set. You can see that you can write it as integral of f of x dx, where on the domain of h of x being in the domain of A. Okay. Then we can approximate these two equations. We can approximate. For approximating expectation, I can write it as 1 over n summation of h of xi for I from 1 to n. What do I mean by xi? Let me sample n x's from my PDF. So I have the dense distribution. I can sample from it, right? Let me sample n. The more the n, the more the sample size, the better the approximation. Okay. Now I can approximate expectation by average. So I'm approximating mean by average. Okay. This is called Monte Carlo approximation. Also, I can approximate probability of h of z belonging to some set A, domain A, whatever. You can write it as 1 over n summation of I, h of xi being in A. What is I? This is indicator function. If h of xi belongs to A, it's 1, otherwise it's 0. Indicator function. So I count how many times it belongs to A, and then I average it, 1 over n. Okay. So this is Monte Carlo approximation. And sample mean and covariance. So in equation 34, you can see that mean, you can write it as, you can see it as the average. It's called, sorry, when you have n samples, you can have the average of them and you can consider them as the mean. Okay, this is called sample mean. Why? Because we are using the samples. Okay. You can also have sample covariance or sample covariance, they call it. So it's because we are having xi minus mu times xi minus mu transpose this summation 1 over n. I think we saw that a lot in high school for scalars. When it is a scalar, this becomes xi minus mu squared, right? This covariance. However, when it is a vector, It becomes xi minus mu and xi minus mu transpose. This is a column vector, xi minus mu. Xi is the column vector, mu is a column vector, xi minus mu is a column vector, xi minus mu transpose is a row vector. A column vector times a row vector, what is it? It becomes a matrix. Therefore, it's a d by d dimensional matrix. Sample mean, however, is the average of n d-dimensional vectors. Therefore, the mean is also d-dimensional vector, right? And also, this is biased covariance. For this to be unbiased, what do I mean by, we talked about bias, right? For the estimation of covariance, these are estimations, right? Estimation of covariance, estimation of mean. For the estimation to be unbiased, the denominator should have n minus 1. Its proof is simple. You can Google it. Now, linear projection. This is crucial for a statistical machine learning. Linear projection. Almost all of the linear models in machine learning use linear projection. Almost all of them. An example is PCA. PCA uses linear projection. So what is that? First off, column space. The names might be scary, but the concepts are very easy. Just bear with me and you will see. Okay, consider P basis vectors. What do I mean by basis vector? Every space can be determined by several basis vectors. For example, in this 3D dimensional space, in this space of the room, you have 3 basis vectors, x, y, and z, right? In 2D, you will have 2 basis vectors. In d-dimensional Euclidean space, you will have d basis vectors. As what do I mean again by basis vector? Every point in the space can be represented as a linear combination of these basis vectors. What do I mean by linear combination? Assume in this space, here is the origin. For this point, I can say how many times should I go in this direction? How many times should I go in this direction? How many times should I go in this direction to reach to this point? So I'm having a linear combination ax, by plus cz, a linear combination of the basis vectors. We can define now I have p basis vectors. We can define a p-dimensional Euclidean space by these p basis vectors. Okay. As I said. For example, 2 vectors define a plane, right? 3 vectors define a 3D space. Now, it's just terminology. The p basis vectors span the p-dimensional Euclidean space. The name is scary, the concept is easy. So this is a space, the 3-dimensional space. This space is spanned by these 3 vectors. It means that I can represent every point in this space by a linear combination of these 3 vectors. Okay. Or you can say this space is spanned by them, or these basis vectors span that space. Okay. Now consider the p vectors, the basis vectors, u1 to up. Okay. Assume each of them is d-dimensional. So I have p vectors, each of which is d-dimensional. If I put them or stack them column-wise next to each other, it becomes a matrix U, right? And the dimensionality of U is d by p. It means d rows, d columns. Okay. The space, now another terminology. The space spanned by the columns of U. What do I mean? Consider the columns of the matrix U. Now consider them, these columns, as basis vectors. They define some space. This space spanned by the columns of matrix U is called the column space of U. Okay, is it clear? The column space of matrix U, denoted as column of U. Column of U is a span of U1 to UP. It's a space, right? In other words, the space whose bases are the columns of the matrix U is called the column space of U. Right? So we just defined some terminologies. Now linear projection. Consider a data point X, which is d-dimensional. Right? When I say RD, it means d-dimensional vectors. When I say RD1 times D2 means a matrix with D1 rows, D2 columns, right? The aim is to project this data point, d-dimensional data point, onto the vector space spanned by P vectors. What do I mean? What is the space or vector space spanned by P vectors U1 to UP? What is the dimensionality of this space? Consider a space whose basis vectors are U1 to UP. What is the dimensionality of this space? P, right? P, because I have P basis vectors, right? Consider this such a space. I have a d-dimensional vector. I can project that d-dimensional vector onto this p-dimensional space. Usually, p is much less than d. The dimensionality of this space usually is less than that d, usually. The vectors, again, I am putting u1 to up column-wise next to each other to have the matrix U, which is d by p. Right? Again, I have a column space of U. Now, if P is less than D, it might be equal to D, right? If it is less than D, this space that I'm projecting onto is also called subspace. Sub standing for P is less than D. Sub is below, all right? Subspace. Because I'm projecting from high dimension to low dimension. And as it is linear, they usually call it subspace. If it is non-linear, they might call it submanifold, something like that. Okay. The projection of X, d-dimensional X, onto this p-dimensional column space is this, equation 38. Okay. So U transpose X does that, projects X onto the column space of U. I can prove it for you. Intuitively, you can understand it. What is, unfortunately, I can't try to understand what I'm saying. What is X? D-dimensional. D by 1. D by. Hopefully, the difference of D and P is recorded correctly. X is D by 1. What is the dimensionality of U? Is D by P. Right? What is the dimensionality of U transpose? P by D. So P by D times D by 1, the whole thing becomes P by 1, right? According to the matrix multiplication. So this, the whole thing is P dimensional. I denote this U transpose X denoted by X tilde. You can call it Benjamin. I call it X tilde. It's P dimensional, according to what we just analyzed, right? So X was D dimensional. The column space of U was P dimensional. The result is P dimensional. So I'm projecting a D dimensional vector onto a P dimensional space and it became P dimensional. Right? This is projection of X onto the column space of U. Now I can reconstruct it back, okay, to become D-dimensional again. For this, I just multiply U, not U transpose it this time. U by the projection. What was the projection? X tilde. I can replace it by U transpose X. So I have U X tilde, or in other words, U transpose X. It projects it, it reconstructs it back. I denote it by X hat. Okay. And this is D-dimensional. Proof? Simple. X is D by 1. U transpose is P by D. U is D by P. Right? And now I will tell you the intuition of what is projection and reconstruction by this figure. Consider this two-dimensional space. Here, D, dog. D is 2, right? So my X here, I'm showing it here, is 2-dimensional in this two-dimensional space, right? And so my column space is 1-dimensional, right? This is column space, 1-dimensional, a line. Why is it passing through the origin? Because by the way, you know that all the spaces in mathematics have to have vector spaces, have to have origin in them. Why? Because we know that the linear combinations of the vectors need to be in the space. And one of the linear combinations is x minus itself. X minus x becomes 0. It has to be in the space. Therefore, origin must be in the vector space. This is column space is a space. The two-dimensional space is also a space. Both of them need to have the origin. And they are passing through the origin here. Okay? Now, this two-dimensional point, I'm projecting it onto this one-dimensional column space. A projection needs to be orthogonal, right? So I project it, it becomes here. This point becomes in the column space becomes a scalar. Do you agree? The column space, which is one-dimensional, that scalar is the distance of this from the origin. Right? Do you follow? This is U transpose X. This is the X tilde. That's one-dimensional. Two-dimensional became one-dimensional. Now the beauty is here. This point, interestingly, I can see it in the original two-dimensional space. This point, which I can see it in the one-dimensional space, at the same time, I can see it in the two-dimensional space again. Right? Here it is, two-dimensional space. I can see it. This two-dimensional point is the reconstruction of it. Okay? As you see, the reconstruction is not necessarily the point itself. You might have some error. You will have some error of reconstruction. Right? The point itself is here. The reconstruction in 2D space is here. Yes.
Sorry, maybe just a little confused at that point. So when you project it onto the line, right?
Yes.
I guess you just ignore the 2D space and you're just looking at the line itself. You should only have like essentially one number, essentially.
Yes. So this column space, ignore the 2D, rotate it, and it becomes one line. The distance from that point to the origin, which is I have shown here, is the coordinate of that point in the one-dimensional column space.
So don't you technically lose the information?
Exactly. We are losing information in projection. That's why we have error of reconstruction. When P is less than D, we have some loss of information.
So like when you
kind of compress, we are compressing it.
When you're projecting it back into 2D.
We are not projecting it, that we are reconstructing it. Yeah, you can see it. Okay. Yeah, we are reconstructing it back in the 2D, but it doesn't come where it was.
Okay. I was just thinking maybe all the possible points form a circle around the origin. One of the points is where it started out at. But
you mean here? Okay.
Yeah.
No, they have different projections here on the line.
Okay.
Right? Also, there is one case that the reconstruction becomes exactly the original point, or the reconstruction error becomes 0. What is that? In some cases, x hat becomes equal to x. The reconstruction becomes equal to original point before projection. What is that case? What?
P and D is.
When P, one case is that, yes, when P equals D, I guess, yes. What does it mean? You project it to the same two-dimensional space and then you project it back. Well, do you know what that means? This is 2D. Consider another two-dimensional space, but it might be rotated something, right? Not necessarily the same space, might be rotated. When P equals D, it simply means that rotate it somewhere, rotate it back.
So that means reconstruction will lose not the information.
Yes, in the case that P equals D, we are simply rotating. To some. We have some rotation, or we rotate it back. Okay. we'll have not loss of information. There is another case. When won't we have any loss of information, even if P is less than D? Exactly. The point is already on the line. Point, you can see it in the column. The point exists in the column space. If the point is already on the column space, its projection was here again, although it becomes one-dimensional. When you reconstruct it back, it becomes two-dimensional, but becomes exactly the same as before. When it is on the line, right? Okay. And this is a figure that we had. And as we saw, we have some reconstruction error. So here in this figure, for example, I have some X. I project it onto the column space and reconstruct it back. I will have X hat. So there is some difference between X and X hat. I'll call it residue or error. X minus X hat. PCA, you can formulate it in different ways. One of the formulations is minimization of this reconstruction error. I don't know if I told you this or not. All machine learning is optimization, plus some other things, plus probability and linear algebra. Optimization plus probability and linear algebra and some statistics becomes machine learning. Okay. So we are always minimizing or maximizing something in machine learning. Here we are minimizing the reconstruction error. If you do that, it becomes PCA. We'll see that. Centering matrix. Okay. Consider a matrix A, which is alpha by beta. Alpha by beta. Then it is represented by its rows in this way. A1, assume the rows are A1 to A alpha. Why do I denote it by this? This is A1 to A alpha column, stacked column wise, but I transpose it. So it becomes rows. A1 to A alpha, because I have alpha rows. Also B1 to B beta as the columns. Okay, where AI is the ith row, BJ is the jth column. Now I have left centering matrix. Left centering matrix is defined, the centering matrix is this, defined as 41. But when the matrix is rectangular, I will have left and right centering matrix. When it is a square, I will simply have a centering matrix. Here I have, in general case, I have rectangular matrix. Therefore, I have left and right centering matrices. The centering matrices are used for removing the mean. So I have some data points. I want to remove their means. But the question is, do you want to remove the mean of rows or the mean of columns? Or both? Right? Rather than, let's consider a computer program. Rather than having a for loop, and in each loop, I remove x minus mu, x minus mu, x minus mu. I can do it in one shot using linear algebra, using matrix multiplications. And I'm using centering matrix for that. To do the whole for loop in one shot. So the left centering matrix is H. Usually we denote it by H or C. H is identity matrix minus 1 over alpha, 1, 1 transpose. 1 is a vector of ones. 1, 1 transpose becomes the matrix of all ones. It's different from identity matrix. Identity matrix has only 1 in the diagonal. Right? And this I here is alpha by alpha. Now, the H becomes alpha by alpha. Now I can have HA. H is alpha by alpha, A is alpha by beta. So the whole thing becomes, again, alpha by beta. And if you do that, it simply removes the mean of rows of A. So I have rows. Every row is a row vector, right? I can remove the means of the rows from it. If you are a Python coder, it means your A is a matrix, a NumPy array. It is A minus NP dot mean of A axis equals 0, like that. So you're having the mean of the rows Then you're removing, the rows from the A stuff. This is exactly what it does in linear algebra. Okay.
Why do we want to remove the mean?
A lot of times, in PCA, for example, a lot of times in machine learning, we need to remove the mean. Sometimes, why? Because we will see that in PCA, if you don't remove the mean, it will ruin the algorithm. Many times in machine learning, we have to remove the mean as a pre-processing. So also, right centering matrix is the same as a left one, but we have 1 over beta, and this identity matrix is beta by beta. Okay, and then I will have AH. A is alpha by beta, H is beta by beta, AH becomes again alpha by beta. This time, the means of the columns are removed. Okay, we use this more often than HA. Why? Why do we use this a lot? Because usually in machine learning, in contrast to coding languages such as scikit-learn, in scikit-learn in coding languages, they usually put data instances row-wise. In machine learning, in the theory of machine learning, we usually put data instances column-wise. Therefore, we have data points as columns of a matrix. We want to remove their means. Therefore, we usually use AH. Okay. We can have double centering, removing both means of rows and means of columns. However, we should be careful. When we do that, we are removing the total mean twice. We need to add the total mean once back. What do I mean by total mean? The mean of the whole elements. Right? So HAH does that. Removes the mean of rows, removes the mean of columns, adds back the total mean. Right? Here is the formulation. You can take a look at that. And so simply summary. HA removes the mean of rows. AH removes the mean of columns. HAH removes the mean of rows, then mean of columns, then adds back the mean of total. We use that a lot when we are dealing with kernels. We want to double center a kernel matrix. We'll see that. We'll see that. If you don't know what kernel is, don't worry. We'll talk about it. Centering matrix has some properties. It's symmetric. Why? Here is the proof. H transpose, you can write it as this. I'm using the definition of H, the centering matrix. Transpose, I can apply it on, I use this a lot. I can apply the elements when I have summation of several things, transpose, and I can have summation of transposes of them, right? So I will have I transpose minus the second thing transpose. The second thing, 1 over alpha is scalar comes out. We'll have 1 transpose transpose. And when I have multiplication, that was summation. When I have multiplication, transpose reverses the order. Okay. So I have 1. So I have Benjamin Jack transpose. It becomes. So I have Benjamin times Jack, the whole thing transpose. It becomes Jack transpose, Benjamin transpose. Okay. So here I have 1 transpose, which becomes 1 again. Then I will have 1 transpose. Interestingly, it's the same as what it was before. And this is H. So H transpose is H. Therefore, H is symmetric. The centering matrix is also idempotent. What is idempotent? Means that no matter how much you multiply it by itself, it remains the same. H times H times H, K times it becomes H again. Proof. Consider H, and then we can have induction, right? H and H. If you multiply the sides together, you will get this. By the way, why is 1 transpose Y here alpha? Why is it alpha? Because 1 here is alpha by 1. Yeah. Then 1 transpose becomes 1 by alpha. And I have alpha ones added to each other. 1 plus 1 plus 1, alpha times. It becomes alpha. Then I'll get these cancel each other, it becomes h again. When h times h is h, multiplication for k times also becomes h, right? Norm. Consider two vectors, d-dimensional, x and y. Their inner product, also called dot product, is defined as this: x transpose y is summation of multiplication of corresponding elements. The result of inner product is always a scalar. I think the inner product of vectors you already knew. It's easy. However, we also have inner products of matrices. Okay. So what is the inner product of x and y? Both of them are d1 by d2, the same dimensionality. And what happens? It's trace of x transpose y. What is trace? Trace is defined as this. Trace of a matrix is the summation of its eigenvalues. Equivalently, it can be proved that trace can be seen as the summation of diagonal elements. Diagonal elements. Note that the input of trace is always a square matrix. It can't be rectangular. Therefore, I have a diagonal. Now I can add the diagonal elements. This is equivalent to summing the eigenvalues. This is trace. Trace of matrix. What is the philosophy of the trace here? Why don't I have trace when it's the inner product of vectors? Can you tell me? Why do I have trace here? Very easy. Don't worry. Don't think complicated. Because I told you that what x is d1 by d2, y is dy by d2. X transpose y becomes d2 by d2, right? It's a matrix. So x is a matrix, y is a matrix, x transpose y is a matrix. A few minutes ago, I told you the result of inner product must be scalar. So for making it a scalar, I use trace. Right? Therefore, I don't need trace for vectors. You can put trace. Trace of a scalar equals itself. Right? And it's defined as summation of multiplication of corresponding elements. Norm. Let's define norm. The function this denoted by this. This is norm. It takes a d-dimensional vector. It can also take a matrix, and it outputs a scalar. It's a norm if it satisfies these four characteristics. What are these characteristics? One of them is the first one. Norm of x is always non-negative. It can be 0, it can be positive, it can't be negative. Second one, a times x, a is a scalar. Its norm, you can bring a outside of the norm, however, with absolute value. Why do I need absolute value? What? Exactly, because of the first property. Norm is non-negative. What if a is negative? Must be non-negative. And norm of x is 0 if and only if x is 0. So if x is 0, its norm is 0. If its norm is 0, x is 0. Two-sided. Lasting triangle inequality. For this to understand, consider this example. Unfortunately, I can't draw, but consider a triangle A, B, C, where B is the vertex above. So A going up, B going down against C. There are two paths, one from A to C, path actually. The other path, it goes from A to B, then B to C. So there are two paths, A to C, and the other path A to B, and then B to C. I have a donkey standing in the point A. And I have some food in point C. The donkey has two paths to go toward the food. Which path does the donkey choose? Can you tell me? What?
Shortest.
The shortest, which is A to C. The donkey understands that A to C is shorter and A to B is B to C. Right? That's why in either Persian or Arabic, this triangle inequality is also called qaziyatul himar, which means the principle of donkey. If the donkey understands that this is shorter. Right? It's obvious what is triangle. And also these are used for defining distance metric, because you can see norm, you can use it for defining distance of the point from the, for example, when you say norm of x, it's just the distance of x from the origin. Important norms for vectors. We have LP norm. LP norm of x is defined as this. Absolute values of the elements to the power of p, sum them up, then the whole thing to the power of 1 over p. P is greater than or equal to 1. Two well-known LP norms are L1 norm and L2 norm, where p equals 1 and 2, right? So for L1 norm, it's just summation of absolute values of elements. L2 norm is summation of squared elements, but the square root. As you see, in L1 norm, I have absolute value. If D is 1, it becomes absolute value like this function, right? And my hand is showing. And it's not a smooth, the origin, right? Therefore, L1 norm is not a smooth, not differentiable at some points. But L2 norm is completely smooth, it's quadratic. There is one important, by the way, we have some other norms such as nuclear norm and this is, but out of the scope of this course. For matrix, Frobenius norm, one of the most important norms for matrix. As you see, it's summation of squared elements, but the square root. Its format is very similar to the format of L2 norm for vector. However, be careful. We also have L2 norm for matrices, which is different from Frobenius. Okay. L2 norm of matrices are usually used in pure math, not here. We have quadratic forms using norms. So squared L2 norm of x, you see that's x transpose x. For matrices, squared Frobenius norm. You can see it as trace of x transpose x. This formula is used a lot. You can put anything rather than x. A squared L2 norm of Benjamin becomes Benjamin transpose Benjamin. Rather than Benjamin, you can write it an expression. What do I mean? A squared L2 norm of y minus z becomes what? Y minus z transpose y minus z. Then this y minus z transpose becomes what? Y transpose minus z transpose. And you can multiply the terms to each other. You will have 4 terms. The quadratic form is like a bowl on here. If you see it from above, it becomes like these lines. In each line, the function value is the same. Now, this is very beautiful. I say this, and I think then we can conclude this session. What is the definition of derivative? Can you tell me? What is the definition of derivative? Derivative. Well, slope, yeah, slope. What is the slope saying actually? What is the interpretation? Change, exact. Assume I'm saying that derivative of Benjamin with respect to desk. What does it mean? It means change the desk. How much does it impact or change Benjamin? Right? So now let me tweak desk. Let's see how much Benjamin is tweaked or changed. Okay. Now consider the derivative of a scalar with respect to another scalar. What happens? Let's tweak that scalar. So the derivative of A with respect to B, both the scalar. Let's tweak B. Let's see how much it changes A, right? How many changes do we have here? One change. Therefore, derivative is one-dimensional. Derivative is also a scalar. Derivative of a scalar with respect to another scale is a scalar. We learned that in high school. Now we are in university. Let's make it complicated. Derivative of a scalar with respect to a vector. A with respect to B, A is a scalar, B is a vector. What should I do? I should tweak each of the elements of B one by one. I tweak the first element. Let's see how much it changes A. Second element of B, let's see how much it changes A. Third, fourth, right? If B is d-dimensional, how many changes do I have? D changes I have. Therefore, the derivative is also d-dimensional. Now let's make it more complicated. Derivative of A with respect to B, A is a scalar. B is matrix. Okay. Assume my matrix is 3 by 2. Let's tweak every element of B. Let's see how much A is changed. How many changes do I have? The matrix is 3 by 2.
3 by 2.
Exactly, we have 6 changes. 3 times 2, right? We have 6 changes. Therefore, the derivative, you can see it as a 6-dimensional vector or 3 by 2 dimensional matrix. 3 by 2, 3 rows, 2 columns, right? Now let's make it more complicated. Derivative of a vector with respect to a vector. A with respect to B, A is 2-dimensional, B is 3-dimensional. Let's change or tweak every element of B. 3 elements, right? Every element of B I change, it impacts 2 elements of A. How many changes do I have? 3 by 2, 6 changes I have, right? Therefore, I can see this derivative as either a 6-dimensional vector or a 3 by 2 dimensional matrix. Derivative of a vector with respect to a matrix, what does it become? It becomes a tensor, rank 3 tensor. So, in summary, derivative of a scalar with respect to a scalar is a scalar. Derivative of a scalar with respect to a vector is a vector. Derivative of a scalar with respect to matrix is a matrix. Derivative of a vector with respect to a vector is a matrix. Derivative of vector with respect to matrix, rank 3 tensor. Derivative of matrix with respect to vector, again, rank 3 tensor. Derivative of a matrix with respect to another matrix, rank 4 tensor. Right? Now, also you understand the dimensionality of derivative. So, from now on, if you have something, maybe derivative of x with respect to y, x is d-dimensional, y is p-dimensional, you should expect that this derivative becomes a matrix d by p. Otherwise, your derivative is wrong. You can check whether you calculated the derivative correctly or not within this technique. Okay, what is left? So we talked about this, and some other things are left, and I think it's not much, like gradient Hessian and some Rayleigh-Ritz quotient, which is used a lot in statistical machine learning. PCA, FTA, all of these, their optimization problems are Rayleigh-Ritz quotient, optimization of Rayleigh-Ritz quotient. And then we'll talk about eigenvalue problem and singular value decomposition a little bit. And then we'll move on to overview. Okay, thank you very much.